Hi, I'm Luis Fernandez, a researcher at Berkeley Lab specializing in Windows. This video will focus on two topics that affect a Windows energy efficiency: temperature-driven heat flow and solar radiation. There are three modes of heat flow relevant to window heat transfer. First, conduction occurs when heat flows through material from a warmer area to a cooler area. Convection occurs when heat is transferred due to the movement of fluids, such as between the bulk of the air and one of the window surfaces, or in the space between two glass layers in a double-pane window. Finally, surfaces emit and receive long-wave infrared radiation according to the Stefan-Boltzmann law. The heat flow through this window can be represented by a resistance network. Resistance to the conduction of heat through the glass is placed between the two glass surface temperatures. Between each glass temperature and the surrounding air, we have thermal resistance for convection and radiation in parallel. This equation models the total heat flow through a window due to these three forms of heat transfer, defining heat transfer per unit area. The U value of the window, which characterizes heat flow due to temperature differences, is obtained by solving for the resistance network. This factor represents conduction, where D is the thickness of the window glass and Kg is the conductivity of glass. The convection coefficients HCI and HCO are standard and defined in units of watt per meter squared per Kelvin. Using this approximation, we can define similar coefficients for radiative heat transfer. Because radiative heat transfer is not linear with respect to temperature difference, this mode of heat transfer will become more dominant as the temperature difference increases. Thus far, we've characterized heat flow for a section called the center of glass, which is far away from the frame. But heat transfer conditions closer to the frame and at the frame itself are different. So, to calculate the U value for the entire window, we would need to take an area-weighted average of the U value for the center of glass, the U value for the edge of glass, and the U value for the frame. When solar radiation hits a window, it can be transmitted, reflected, or absorbed. These results can be quantified as fractions of incident radiation, transmittance, reflectance, and absorptance, and can be defined across the whole solar radiation spectrum, or just for the visible part of the spectrum. Since we're discussing energy flows, this video will focus on the whole spectrum. Returning to the main equation, we can add this term representing the energy transmitted through the glass when solar radiation hits it. To account for energy that is re-radiated to both the interior and exterior of the window, we add the coefficient N, or the inward flowing fraction, representing the fraction of the absorbed energy that ends up inside the space. This quantity is called the solar heat gain coefficient. For most practical purposes, the U value and the solar heat gain coefficient help to characterize a window's energy efficiency and the comfort it might add to a room. While this video focused on a single-pane window, many windows are more complex, with additional panes, coatings, or other variables. At Berkeley Lab, we've developed software applications called Window, Therm, and Optics to help you perform these calculations on any window. Learn more about this software at windows.lbl.gov/software. We hope this overview has been helpful. To learn more, visit Berkeley Lab or view the next video.